I did a bit of background research to try to figure out exactly what ionization meant to this center of excellence. And it was broken down into two separate questions. What are the sources of reionization? What first created such massive amounts of energy? And when did the veil of the cosmic dark ages rise, and how long did it take? So I really can't do an ASTRO 3D meeting without showing this lovely simulation that the Dragons team put together. I think this is kind of the penultimate simulation that has come out of ASTRO 3D, at least this visualization. It's from Paul and Simon in particular. The neutral hydrogen is highlighted here in red, and we're going through the epoch of reionization. So these ionizing sources in white are popping out, the very first stars and galaxies, and their harsh light is reionizing this neutral hydrogen, thereby destroying that from which they were born. So how do we measure this epoch of reionization? Well, hypothetically, it should be everywhere that we look. It's a cosmological thing, so it's in every single direction. And since cosmology is isotropic and homogeneous to first order, we should see it everywhere the same way. However, there is everything between us and the epoch of reionization. Every star, every galaxy is a foreground. And so we have to remove an entire universe's worth of galactic and stellar mass in order to get to the epoch of reionization. So we have to be really clever about how we try to measure this. And this has been the theme of ASTRO 3D since the beginning. So one way you can be clever is you can say that all of the stuff between us and the epoch of reionization is essentially synchrotron emission, an electron spinning real fast along a magnetic field, releases a certain wavelength of light, and that has a very characteristic look as a function of frequency. In log space, it's smooth. And so you can use this fact and the fact that the epoch of reionization is bubbly. So that 21 centimeter light coming from the neutral hydrogen from that hyperfine transition will end up looking bumpy as a function of frequency. And that's from all of those bubbles coming on and off. And so all you got to do is take Fourier transform, right? You should be able to separate all of that synchrotron emission from this lovely epoch of reionization signal. You'll find out later, it's not quite that easy. The other thing you can do is you can try to look at something bright that was turning on during the epoch of reionization, like a quasar, or now that we have JWST, a galaxy, really like one of the first galaxies. And you can use your knowledge of the sources to try to back out what was happening during the epoch of reionization. These two ways of looking for the EOR are complementary because one is very global, right? One is looking at statistics of a global signature or the various bubble sizes, and one of them is looking at a long line of sight. And so together we can get a comprehensive picture of what was going on back then. And I did the same thing as Emma. I took that ASTRO 3D publication list and I tried to break down what belonged in the ionization group. And so I looked up something that had ionization in the abstract. And then I went through and painstakingly hand-selected things that I knew would not fall into the ionization category, but just happenstance had the word ionization in there. And what I came up with is this lovely set of papers. There have been a very consistent amount of ionization papers throughout the ASTRO 3D history. You will notice that there is a bit of a dip during COVID times. I think that's to be expected. And I'm sure if you looked at the other themes, you'd see something similar. But, we picked back up, got back on track after COVID. And despite that, we've had fantastic citations throughout the history of ASTRO 3D. And I'm really glad that I did the painstaking job of hand selecting things that I knew fit into the ionization category, because it let me see some overarching themes regarding ionization. So as a function of time, starting from 2017 through 2024, you always had MWA. You always had these radio interferometers. They've been on the ground the whole time. So they've been collecting data, producing papers. You've also always have had some sort of theoretical component, simulations, dragons, Meraxes, 21 centimeter fast. So these have been consistent throughout ASTRO 3D. Roughly 2018, you have a surge of something called a global experiment. So instead of doing a radio interferometer, you're trying to get just that global signal of basically a temperature, one single temperature of the epoch of reionization. And that turned on after the EDGES result in 2018. And then you have some ALMA papers coming through looking at what was happening during the epoch of reionization. And then, of course, you have JWST coming into the playing field. You have the JADES, fresco, glass, pearls, all these various surveys and data sets are now available. And then towards the end here, we also have the Very Large Array X-Shooter program, which was one of the largest programs looking at quasars. It was like 250 hours worth, truly impressive. And that's, I'll get to the end as well. So looking at publications in ASTRO 3D as a function of these like little sub-themes, I then went through the abstracts, did some searching. I'm just putting this one up here because I thought it was cute. There was 100% of reionization spelled with a Z in the abstract and 4% with reionization spelled with an S in the abstract. So this just kind of gives you the idea of the error bars I'm working with here, because that doesn't make any sense to me. But you can blame ADS for that. For abstracts which had observation listed, there were 75%, simulation 34%, survey 32%. And of course, this isn't truly indicative of whether something was observation or simulation, because sometimes you have those words in your abstract to try to get as much exposure as possible. 27% of abstracts had the word JWST in it. 12% had the word Murchison for Murchison wide field array. 11% had square kilometer array, 5% had ALMA, and 4% had X-Shooter. 32% had 21 in there. I put 21 for 21 centimeter, but some people put a hyphen, some people have a space. It's all over the place. 17% had the word quasar and 7% had the word global. And I also utilized the machine learning power of ADS to group into a reference network and an authorship network. So the reference network is just the groupings that ADS thought were in this little subset of ASTRO 3D publications, and it pretty much got it right. You have JWST style stuff in the purple. You have quasar related things in green. Yellow, you have Murchison wide field array things, power spectra. And red, I think you have theory, though it's not quite as clear cut. The authorship network was really fun to look at. So it groups people based on who's citing who. And so you can kind of see this purple is indicative on the authorship network of people in theory. People in theory cite people in theory, cite people in theory, and so on and so forth. So you get these little islands of people, which is I think is really interesting. So that's kind of it for the publications as a whole. And now I'm going to get into each of these specific sub-themes that both ADS and I picked up on. And we'll kind of go through the recent things that have happened over the past couple of years to get an idea of where we've ended ASTRO 3D. So we'll start with the Murchison Wide Field Array, the thing that has been around since the dawn of time, nearly. It started out with 128 dual polarization antennas in the outback. Now there's 256. And it's produced petabytes of interferometric data, all of which you can access on the ASVO if you like some pain. Thanks to Kath, Regina, Ash, and Mike for the suggestions on in the next slides. So I'll start off with Mike Creel's diffuse galactic work, kind of just to give you an idea of the things that need to be done in order to see the epoch of reionization. You have to really understand things that are nearby. So you have to understand your own galaxy, really. Mike made a beautiful spherical harmonic map using the Engineering Development Array 2, which is at roughly 160 megahertz. And really what he found was it showed extreme differences with maps made at gigahertz, using gigahertz surveys that were scaled down. And that's what we had done for the longest time. We just scaled down something from gigahertz frequencies. But looking at it in the megahertz frequencies, our galaxy is doing much different things than expected. And this was truly important for epoch of reionization research. Jack Line made the Woden simulation. Woden doesn't stand for anything. He just thought it was cool. So it's named Woden. It's a GPU-based radio interferometer simulator, which truly required really difficult work to get going. It took him roughly the whole time to get it going. And on the left there is that I'm actually switching between two images. I don't know if you can tell, if the eagle-eyed people in the room can see. And that's just how fantastic Woden does. So we have real data switching between simulated data. And this is crucial for epoch of reionization research. You need to have something that's spot on. And this is understanding the instrument. This is understanding the sources in the sky. It's everything. And Jack recently wrote a paper that validated our pipelines using these simulations. So it's a full end-to-end simulation to try to understand what the statistics are doing at the end. And it was really important to do that because there's certain correlations that you don't know exist until you look hard enough. And then I took the wonderful intellectual power of Mike and Jack, and I combined it. So I took Woden and I put in that wonderful diffuse map to simulate the galactic plane and what it's doing for the MWA. So here on the left, you have the EDA2 map setting over the course of the night. And then on the right, or in the middle really, you have what's happening in an interferometer. So an interferometer is a Fourier-based instrument. If you have something hard going over an edge, you're going to get aliasing, and that's what we see here with the galactic plane. And on the bottom right, you have real data flipping between what happens when you don't subtract this galactic plane put through an interferometric simulation and when you do. So you can see the galactic plane contribution. It actually affects most of the image and needs to be subtracted. This was by far, I think, my favorite work done in ASTRO 3D, and that's because I basically got to do it with these people. So I got to do it with Jack and Christine and Mike and Jaden. And we were kind of all in the office together, and that was a lot of fun. So we're all part of ASTRO 3D, and this was a great way to collaborate, I think. Aman will be talking right after me, so Aman is talking at 4 p.m. I do want to have a shout out though, because he's doing great work on checking out what the instrument is doing. From what you could tell from Jack's simulation, where you have to flick through and you have to get that precise, you really have to understand what the instrument is doing to get that precise. And what Amon has found is that the MWA, even as simple as it is, has deviations towards the edges of its primary beam, which are very detrimental to epoch of reionization measurements. And Amon is even going beyond the EOR and looking at what it does to rotation measure as well. So these are things that I think will become more important as we get into the SKA era, when we start really hitting, the most precise measurements possible. We're going to need to understand the SKA to its fullest extent. So do check out Amon's talk next. Redeema is doing beautiful work looking at the most disgusting MWA data and cutting it out. So when you get visibilities, you don't know if they're going to be good or if they're going to be bad. They're just numbers. Numbers is a function of frequency. You can make images, but that costs computing power. So how do you cut things from your data set without looking at them? That's what Redeema is doing. And she has found that she needs, I think it was like 13 different metrics for selecting data. So there's 13 ways the data can be bad. And this is critical for EOR research, and she's cutting almost half of the data. And so that's in review right now. Ash did something truly incredible. She built an instrument basically from the ground up. I do not envy her for all of the engineering that she had to do to get the CRAM tile working, the central redundant array megatile. It's basically an MWA tile, but on steroids. It's huge. She is using that CRAM tile to create a different beam. So you can see the MWA beam on the left there in the red and blue, and then the CRAM tile on the right. And you can see they're vastly different. And she's looking at taking baselines, or taking a baseline between this CRAM tile and an MWA tile and saying what happens to the data when you do that. This will be the only power spectra I show, I promise. It's on the bottom right here. You don't even really have to understand it, just look at the pretty colors. The blue in the far right means that doing an MWA CRAM crossover is doing better. And it's doing better by over 2 orders of magnitude. That is huge. So that might indicate what we need to do in the future. We might need to get creative with mix and matching our instruments. And just pulling all together, shamelessly stealing Kath's slides here. The MWA project has not seen the epoch of reionization, sorry. That's spoiler alert, but we've done so much groundwork in order to build something that's truly robust. We've looked at the sky, we've looked at the Earth's ionosphere, we've looked at the instrument itself, and of course, we've looked at the analysis. And we've tested every single component using full end-to-end simulations. And this has resulted in a huge body of work and a lot of time and effort from a variety of different people. And so we're well and truly on our way using the MWA. Now, on to simulations. Meraxes, Dragons, 21 centimeter fast, oh my. Thanks to Blue for these suggestions. We'll take a look at Blue's paper first. So Blue was looking at a Fisher matrix forecast using both SKA low and JWST, and I think that's a really insightful thing to do, because it's not just the interferometers, it's not just JWST, it's both. Combining both information, both sets of information is truly how we're going to constrain astrophysics and cosmology. And Blue is showing that, yes, of course, you can do much better if you use both data sets. Jaden made this truly disgusting plot. It's wonderful. We call it the spaghetti plot. It's not even the worst one in the paper. It's great. He's looking at a skew spectrum. So instead of a power spectrum, instead of doing a 2-point correlation, he's doing a 3-point correlation and averaging over all various shapes of 3, so all triangles. And it's doing something really weird, and that's because the skew spectrum is probing non-Gaussian entities. Using non-Gaussian entities to describe what's going on in the epoch of reionization will be really important, because the Gaussian stuff is fun. The non-Gaussian stuff, that's cool. That's where we're going to get some real cosmology out of it. And so this is just a foray into that mathematical space. Simon also had a wonderful paper come through. He looked at what was dominating the epoch of reionization using new versions of his simulation code. And he found that it was low mass galaxies that had a higher escape fraction, and massive ones had a very low escape fraction. But which one dominates at what specific time in the EOR, it changes. So you have, I believe it was, lower, it appears as though low mass galaxies are dominating at the beginning, or sorry, towards the end of the epoch of reionization, and high mass ones are dominating towards the higher redshifts, which is a very interesting result coming straight out of theory. And then we have this wonderful talk from Manu coming tomorrow. So stay tuned at 9 a.m. tomorrow to see what simulations say about JWST galaxies, and whether or not they are POP3 or POP2 dominated. The answer will surprise you. I found this very interesting. The plot on the right here, the dashed line is the metallicity transition between a POP3, POP2 as a function of redshift, and you can see that there is a transition, and that Manu is probing it very well, and that it happens at much higher redshifts than I had expected. So I'm excited to see what Manu has to say about that. Now on to a different subset. This is the analog galaxies. So instead of looking all the way back to the epoch of reionization to see the very first stars and galaxies, you can look at galaxies that are much closer, that seem to have the properties that we expect from the very first stars and galaxies, and that we can study these to understand what's happening further in the past. So these are extreme emission line galaxies, or EELGs, and these come from the Bosel survey. So thanks to Anshu for these suggestions here. First up, we have wonderful work from JWST et al. 2024, looking at how the sample set of EELGs that they've selected, how they compare to what is expected from the very first stars and galaxies. On the left, you have a proxy for age, and the EELGs are the dark blue box. The pink and yellow are the epoch of reionization galaxies, and the cyan is the control, basically the current galaxies. And you can see that the EELGs are younger, much like EOR galaxies, that they have a star formation rate that's closer to epoch of reionization galaxies, and they are not quite as dusty, which is also indicative of an EOR style galaxy. So this is just proving that that sample set is truly follows the different sample that we have. Yes. And then Anshu is looking into this sample set, trying to determine what's going on. And what she found was that the companions that these galaxies have, their stellar mass ratio is 3 to 10 times smaller. And that's very interesting. And she has this theory that she has submitted and will be published soon, that it's not, that the ionization channel is actually going through basically one channel. that it's not like it's leaking out of the entire galaxy. It's not like the photons or continuum photons are leaking out of the entire galaxy. They're coming out of a single channel. And that could explain some of the things that she's seeing with EELGs. Now on to JWST, the penultimate infrared space telescope. Thanks to Alex Cameron for these suggestions. We'll have a look at the JADE survey first. Here we have, I'm just showing you the Hubble Space Telescope Grism spectrum for a redshift 11 galaxy from 2016. I'm going to squish it down, and then I'm going to plot on top of it what we get from JWST. You can see just how much more information we're getting. And in fact, what we found with this specific galaxy is that it's an extreme nitrogen emitter. And this JADES sample has found quite a number of these extreme nitrogen emitters. And this paper had both Alex and Kit on it as well. And these extreme nitrogen emitters can actually be explained by nebular-dominated stars. So if you look at the theory for a typical a stellar-dominated star, stellar-dominated galaxy, sorry, and you get younger and then you get hotter, you can see that the nebular emission in the orange is now dominating over the stellar emission. And so they think this is why we have these extreme nitrogen emitters. Kit led some great work looking at a really, really old galaxy, 510 million years after the Big Bang. You can have a look at his Sparkler talk tomorrow at about 9:50. But yeah, this is a truly old galaxy. He got into nature astronomy. Congratulations. Short story is that he found that mergers are happening early. And massive galaxies are happening earlier. So we're kind of changing our understanding of when the epoch of reionization truly occurred. Yu Zhang took some basically JWST and theory, so I put it in the JWST section, but it also counts as theory. He took some analogs from a simulation that were extremely high redshift, greater than 12, and he fit them to try to see how they fit well with the JWST observations in terms of their spectra. And he found that, yeah, his analogs matched up really well from JWST observations, except for the redshift range greater than 16. He needed to employ different physics in order to make that work. Again, indicating that we don't truly understand what's happening at the higher redshifts. And most recently, we've had a very large telescope data from the spectrograph, the X-shooter spectrograph, 250 hours, truly amazing on, I think it's over 30 high redshift quasars. Thanks to Rebecca Davies for these suggestions. We have both Oma and Rebecca have looked at how these quasars are behaving. The takeaway points here are that the low ionization absorbers are more common at greater redshifts, despite high metallicity, which is kind of an odd result. But on the same token, high ionization absorbers are much less common at greater redshifts. So we're getting a bigger picture of what's happening using these line of sight probes of the epoch of reionization. And Rowlands et al. In prep also saw that looking at this large data set of quasars that you get quite the variety of ionization states, which supports the idea that reionization is patchy. And Brad used this data set to do an analysis called the damping wing process for quasars, looking at basically the rate of decay in the spectra. to try to say something about when the epoch of reionization happened. And he found that it was very consistent with previous results. So there has been a lot of things happening for this ionization theme. We've had the MWA, which has been around for quite some time, chugging along as it always does. We've had simulations tell us about what's happening and using observations to make robust predictions about the epoch of reionization. You have the EOR analogues, which we can study in detail because they are much more nearby to try to say something about what was happening in the past. You have JWST really truly came out, and there have been an explosion of papers using JWST to look at the oldest stars and galaxies. And then we've looked at large data sets of quasars to try to probe line of sight epoch of reionization results. So I do want to end early, and I will end on this slide. This is all of the people that I've shown their work today. You'll notice that they're all basically ECRs. And despite the community's best efforts, we don't have another ASTRO 3D style center of excellence coming. And so a lot of the jobs that we've built, a lot of the people that we pulled into Australia are now entering kind of an uncertain future when it comes to funding. So while this is a celebration, this legacy meeting is truly a celebration, I do think we should treat each other with kindness, because some people's jobs might end, and that's really quite sad. But we're all here for you, and we'll all be kind to one another. Thanks.
Thank you, Nichole, for ending on such a positive note. Continuing in kindness, do we have any questions for Nichole from the room? I'm also keeping an eye on Slack. So if we don't have time for your question, I will encourage you to also go ahead and pop it on Slack. But I can already see we've got some over here.
Hello, thank you very much for your talk today. I wanted to ask about this Woden simulation that you mentioned earlier. Specifically, you showed a plot of a simulation where you had kind of a before and after for removing the galactic plane from observations.
Yeah.
By that merit, would you say that Woden gives good indication as to how we can subtract that same galactic plane signature from real observations as well?
Yes, so that was actually real observations.
Okay.
Yeah, it was comparing. So I took the simulation, and so I was flipping between a real observation, which had everything in it, and an observation which I had taken the simulation and subtracted it out of the data. So yes, absolutely it can. And that's truly its power for me. So I've been using Woden to subtract basically any foreground possible that I have some sort of model for in real data. And that's crucial to reducing the synchrotron emission that's leaking up into our very special statistical modes that we're looking at.
Okay, that's wonderful. Thank you.
Yeah. And Emma, I think you're
all right. Okay, Nichole, feel free to outsource to the audience if you want. So JWST has shown that there's star formation is more efficient. It's got higher merger rates. The more massive galaxies, the more efficient. In light of that, I know some of the things that you showed for the 21 centimeter predictions were publications that occurred before JWST.
Sure.
Do you have is there an awareness of what the consequences are for those 21 centimeter predictions now that we know that there's more star formation earlier on?
Yes, and I would say that that's really where the simulation is coming in, taking those observations from JWST and modifying Meraxes or Dragons or whatever to try to match those observations, and then pull those astrophysical parameters and feed that back into 21 centimeter. That being said, 21 centimeter has always kind of had this issue of people saying, when is reionization? Because we built the instruments before we had pretty much any idea. We were like, oh, reionization does that, great. And it happens at redshift 10. Yep. Because it's a round number. So it's kind of always had this issue of arguing about when it's going to happen. It doesn't truly affect the NWA or LOFAR because they have a very wide range of redshifts that they're looking at. So they can still measure different periods of the epoch of reionization, but we're always getting new estimates for how bright it's going to be. And it's unfortunately gone down with time.
Okay.
So we get closer and it keeps going farther away. So yeah. I don't know if someone from JWST has anything to add on that front or from the theory side. Stu does.
So interestingly, I don't think the number of galaxies at high redshift, up to 12 at least, is a surprise to the simulators because those galaxies have been in their simulation. So in terms of predictions for 21 centimeters, I think we know much, much more about the galaxies at high redshift from JWST, but the models, it's not affecting directly what predictions we make for 21 centimeter. It's other uncertainties that we don't have a handle on, escape fractions and things, but.
If there are no further questions, if there is anyone with a hand up and I've missed you, then please. Yeah, hi. If not, could we please thank Nichole for giving us a brilliant overview of ionization?